Hello, welcome back to our series of videos writing a Rust-like programming language in Rust. Language is called Milk. My name's Andy. We're going to try and do... I was going to try and do a chill stream, and then I've stressed myself out by looking at all the to-dos I put in the code. But yeah, we're going to do a nice chill video because we're going to search for the to-dos that we put in that were for writing tests. And then we're going to try and pick one of them or maybe more of them and write some tests around some functions that we acknowledge with these to-dos we should already have tested. And actually fill out the functionality in those functions as well. But the first thing I think we're going to do is I've just realized we wrote all of our type checking code. We just stuck it inside main because get your red, get your test failing, green for get your test passing, and then refactor, right? And this is a part of our refactor part that we haven't done yet. So let's move all our type checks into a function called type check, I guess. So something like this. So we've made a new file called type check, and we're going to put all of the type stuff in there. So we got this type constraint thing and errors like type mismatch and more stuff about type constraint, the actual type check function, and then the functions that are used to implement that. And then I guess we should look at, these are all tests that are to do with type checking as well. Type constraint, combining types. Of course, we combine types, don't we, to make our type checking work. All type. So all of that can go into our new file, and it will need a few imports to work, I assume. Like Miet diagnostic and Miet named source and Miet sourceman. I was expecting more inputs than this. There we are. Yeah, symbol token is from our own code. Syntax tree is from our own code. The parser crate. Leaf token kind. I guess we're going to lose a load of imports from main as well. That are going to be unnecessary, right? Yeah. So we don't need those. And we don't need those. And we messed something up. Oh yeah, of course, we haven't imported type check. And I'm not quite sure why, but we ought to be able to just import type check from type check like so. Yeah, it wouldn't auto-complete that for me for some unknown reason. Right, so let's just check our tests still pass. And also, we better check that it still runs. So if we pass in 4 plus 3, we panic. That's not good. Is that because we haven't actually implemented type checking of expressions? So what if we do let x equal 3? That works fine. And even if we say now print out x. Okay, so that's all right. So it seems to me one of our to-dos really needs doing because there's at least one function that is not properly implemented. So line 93 and line 114 of type check are some things we haven't finished yet. So 93 is this, with a to-do here, as you can see. type checking a syntax tree, and I think it was 114, and that is type another. So basically, there's some things that we haven't finished type checking, haven't finished writing type checking code for, and somehow this has slipped through our test regime, which is a little worrying. Why do our tests pass when we're not able to type check? Okay, I see what we've done here. So I guess what I should do is, there's nothing wrong with what the changes we've made here. Oh, have I missed? I should have done a commit before I did all this. All right, let's see if we can break this into 2 commits. So those changes to main are purely to do with removing. Oh my goodness, we haven't done a proper check-in of the type checking code at all. Because it's not showing up in the diff here as being removed. So we really made a bit of a mess. All right, what are we going to do about this? We can first check in this, whatever change I had not checked in before we did all this. Oh no, this is all just stuff for error checking. All right, this is all type checking code. And if we do it, if we add it and diff all the cached code, we should see all the type checking code appear. So basically, we're going to have to wait a bit longer because this stuff doesn't really work yet before we do a commit. Now, this is terrible. I'd much rather have done multiple commits, but I feel like I'm stuck with it. So the situation is, if we look at our main method, we're doing what is now the correct thing to do, which is we lex stuff, then we parse stuff, then we type check stuff, then we evaluate stuff. But in our tests for the evaluator, which is where most of our tests of like, does the code really work, happens, we're calling eval on the result of parsing, and we're not doing any type checking. And so a lot of these tests just use eval v, so we can modify eval v, and a few of them manually parse, so we need to manually do that ourselves. So let's fix the eval v function first, make it do type checking as well. So I think the way type checking works, if I look back at main, is that we basically make a copy of the syntax tree and we call the type checker on it. And we know that that's probably not going to be how it ends up, but that's how it is right now. So we've already got a vector of a syntax tree. It's actually a MET result. So let's just, for now, let's just deal with any errors by returning immediately. That's not what we do. Oh no, that's not what we do. In here, we deal with errors immediately by just saying this shouldn't have happened. So now we've got this thing called syntax trees, which is a vec, and where we're going to type check it by bringing in our type check thing. We'll pass in input, I think is what we call that file, and we'll pass in an iterator over syntax trees, but not into iter, because we want to we don't want to use up syntax trees because we're going to pass it in here, and we need to do something with the result that comes back. So we'll say type check failed. And this is now going to fail for a load of tests, because that's what we were missing before. So let's cargo test, and hopefully we'll have more indication that stuff doesn't work because we're not finished writing our type checker. So change of plan for this video. We're not going to fix to-dos. Well, no, I guess we are going to fix to-dos, but we're going to be forced to do it because our tests fail, as opposed to because I've written new tests. All right, so let's, I guess, start with the first one. So in type check, on line 93. Special apologies to Jez for not doing good commits. I know that's going to make you sad. It's making me sad too. So, type check tree is not properly tested, and there's at least one type of tree which we're not correctly type checking yet. We could probably make some tests pass by just doing nothing when we type check an operation. But I also think the type constraints on the operations that we currently support are probably going to be reasonably easy to implement. So we may end up implementing this to do. Or rather, implementing properly this function so that our test pass. So let's think about how we're going to test type check tree. Have we got any tests for it yet? No. So what does type check tree do? It takes in a tree, and a file content's just for error handling. So it takes in a tree, and it gives us back the constraints on the result of that syntax tree. So for example, if we get in a leaf, we call type check. Leaf just means like a thing, like a int or a float or a symbol. And it tells us what the type of the result of that expression is going to be. So if we have an int, the type of it's going to be int. If we have a float type, it's going to be float. And if we have a symbol, it's more complicated. It depends what we have to look up that symbol in the environment to find out, which I guess is why this is stuck as a to-do here. So we might work around this by saying like there's some kind of any constraint, or we might do this properly. But I think, yeah, step one is going to be, we don't know what type this symbol represents yet because we haven't done our full type checking code yet. I don't want to gate us behind implementing all things like environments and stuff. And also, so that was the leaf, but then also assignments have a type of unit and statements have a type of unit. So those should be fairly simple. But yeah, type check assignment doesn't only, this type check thing doesn't only tell us what type our result is, it also checks the kind of internals of our thing. Does it actually check out? And so where our actual useful type checking code so far is inside type check assignment, because it checks that the right hand side matches what we declared was the type if we did in that assignment expression. All right, so looking at this, it looks like we shouldn't do type check tree yet. We should do type check leaf first. And let's have a look at how our tests look at the moment. So we've got tests for like combining type constraints together. And we've got somewhere, tests for just like int literals have type int, blah, blah, blah. And then assignments like this. It all looks fine. If you say it's an I32 and you can pass it a 3, that's okay. And then if something goes wrong, it tells you. But we've got nothing, obviously, for symbols. So how are we going to do that? I guess let's just go at the end, but we'll have some code that looks a bit like this. And it's going to be, I guess it's just like type checking symbol gives its type. This is what it's eventually going to look like. So our code is going to look like put a 3 into X, declaring it's an I32. Then what is the type of X? Well, the type of X should be I32. Now, does type check actually return anything? No, it returns like a result of nothing. So we're not calling type check, are we? So we need to do some kind of parsing. Yeah. How is this? Maybe we're not going to actually be able to write nice examples that are made out of real code. Let's figure out what function we're testing. We're testing type check leaf. So let's try calling type check leaf on its own first. So if we call type check leaf, we need to give some kind of file contents, but it's actually, I think it can be, it's not used, so it can be anything. And we're going to give it a leaf token of type symbol. So I think it's going to look like leaf token kind symbol. And the span, I think, is just like where in the document it all goes on, and the symbol. And we're kind of revealing from ourselves here that, that should be an actual string. Like basically type check leaf doesn't take enough arguments for us to be able to look stuff up in an environment and figure out the type of X yet. So there's definitely more work that needs doing here. So this should pass. So type checking failed, I guess we can say. And the point is, the correct answer here is whatever the type of X has been declared as earlier in the parsing or evaluating or type checking, but there isn't any, and we've got no way of passing in an environment yet because we haven't influenced any of this. So for now, the answer is going to be wrong. So we're going to have to replace our to do with another to do, which is to do answer should be found by looking in the environment for this symbol. For now, we say anything goes. So we're going to have to make up, I think, a type constraint, which is any, which at some point, hopefully, we can get rid of again. But for now, or maybe it will come in useful. For now, we're just going to say type constraint any, which doesn't exist yet. It's not about any. So it feels a bit dirty, but I think it's the only way for us to get back to working code at this point. So let's make ourselves this thing called any. And its warning is that we never constructed, but we will in a minute, so that's fine. There must be other problems caused by this, right? Maybe not. Okay, so now let's see if we get a failing test from this test. Evaluating, excuse me. Yeah, type checking a symbol gives its type, which isn't actually true, so we should probably to do actually any. Like I just want something there. Oh, it doesn't like that. I just want something there to tell me that this test doesn't actually. So maybe we should put this at the beginning. I don't want to give myself the impression later when I'm reading back through this that this code is already done. So I just want to name our function in a way that means that we'll remember that this doesn't actually test the thing that it should be testing. And I guess while we're here, we should have other unit tests for this function. Oh, I don't know. I like testing things through code like this normally. And it can't. Yeah, right. So I think we should also. Yeah. So I've written a test that checks the explicit return type of this thing, because in this case we're kind of returning the wrong return type, and I want to be able to test that we're going to return the right return type at the right time. But I think we should also have a test for, like, this thing works. This is the style that I'm mostly using for testing all of this stuff, which is like the code that you wrote, the code that you naturally write for this type of job will still work. So this should just be type checking a symbol does not fail, let's say. So basically, if you write now what is now valid code, which is that x is an i32 and we're putting an i32 in it, and then I'll ask what for x, that should type check. The answer is going to be x and the code is valid. And I guess we should also look for a situation where it's not valid. So maybe it would be this one's definitely going to fail, so we need to ignore this. Type checking, assigning incompatible types. Is an error. Is that how I expressed it? Is an error. Yeah. So it should just be assigning incompatible types is an error. So here it's going to be let x be an i32, and now let y, which is an f64, equal x. And that should fail with some kind of error. So let's just say should fail with an error, and we can just ignore this test because that's definitely not going to pass right now. But I just want it down so that we can. So we've got some model for how we're going to test this stuff when we get there. All right. So now if we run this, all we've done is made it worse by making another failing test. Because our type checking a symbol doesn't fail test. So the nice thing about that is that there's no to do here because this test definitely should pass now and forever in the future, whereas this one is going to change. But also this test doesn't really test anything much because it doesn't actually test the return value of the type checking on that X expression. But let's make this test pass and also this test passed by returning any in this case. So type checking a thing of type symbol should return type constraint any, and we needed to do here actually look up this symbol in the environment. Now, do those two tests pass? They do. And yeah, and now both of our tests that were failing before are failing in the same place, which is at line 94. So we fixed one of our problems. We've still got this, and we haven't tested this return type here, which is also kind of interesting. So let's try and handle both those things. So now we're going to write some unit tests for type check tree. Which are going to, I guess, look a bit like type check leaf. And that's the first one should be, what is it? It was, the return type of that should be unit. No, sorry. The return type here should be unit. So when we're type checking a tree, that is a statement, it should return unit. So I think we can just directly test that. So let's say type checking a statement returns unit. Fine. It should be okay, shouldn't it? Type checking a statement returns unit type. So basically, this is the thing that any statement, i.e. a thing that ends with semicolon, returns what Rust calls the unit type, which is that bracket thing. So type check tree, we better give it a, what does type check tree take? Syntax tree. So a syntax tree of type statement, and inside here, we need to give it a box of syntax tree. Yeah, so I'm not liking these tests that are not... okay, what's this statement going to contain? I guess it's just going to contain a leaf will do us for now. I'm not liking these tests that are not code examples. I much prefer code examples. So let's provide us a leaf token. of kind. Well, how did I end up in there? Leaf token kind. Let's just say it's an int. And the span can be just some numbers, doesn't matter. So if we say please type check this syntax tree, which is a statement, that's just 3 semicolon, right? Then the type that we get back should be unit. Type checking a statement returns unit. That test should pass. Yeah, same number of failures as before. Type checking a statement returns unit passed. I guess we should double check that it's really running by saying it returned F64. That fails because it returned unit, so we're all good. Right, so that's one to-do done. Let's get rid of that to-do then. Type check tree. Yeah, we've tested that return type. But we have another to-do here, which is more difficult, which is what's the type of an operation? No, it's not that difficult, but it is more difficult. Okay, so there's 2 ways we can handle this. We could do it with a code example, or we could do it with another test that's a bit boring like this. I prefer a code example. So what I'm going to say is, I think this one should work. I guess we'll need 2. We'll need a positive and a negative example. So positive example is, if I ask for 19 plus 21 to be put into X, which is an I32, then type checking an assignment of a suitable expression is okay. So basically 19 plus 21 is a suitable expression to be assigned to an I32. But if we try and type check something that is not suitable, it should fail. So let's say assign into an F64 a similar expression, 91 plus 12. Then this should be assigning a wrong type, let's say the wrong type of expression is an error. And then we won't get this right, how we lay out this error message, but we'll get it as close as we can, and then we'll have to fix it when this is actually working. 91 plus 12. And I guess this is going to underline the whole of this expression. Maybe that should be a plus there. I'm not sure. I'm not sure what that looks like, and I'm not sure what Rust will print in this case either. Maybe we should just try making a program and see what Rust prints and see whether we're doing something similar to what Rust does. But it's going to be something like that. Let's make ourselves a little program. How should we do that? Let's go here. No, let's make ourselves a new terminal. Well, let's do cargo new. Bad expression. And edit our new program and make it just be what we said. Let x colon F64 equal 91 plus 12. And when we compile this, we get, so yeah, it's pretty similar to what we said. It says, instead of saying found 91 plus 12, it says found integer, I guess because there's more than one thing and he doesn't want to get into, is this too long to print or whatever, so it just says found integer. So let us also do that and try and be as close, because I think like there's a lot of wisdom in all the error messages that, this should be found expected F64, shouldn't it? And that should be an F there, which is why we were 1 off a minute ago. So there we go. All right. So there's as I was saying, there's a lot of wisdom in those Rust error messages. So let's try and copy them where we can. Like in this case, I think we probably can do this. Let's try and copy them exactly. Where we can't, we should do it, and later on we will do it right. Okay. So these are guiding tests. Are they too difficult, or? This one's going to be quite difficult to do. This one I think we might be able to get past fairly soon. So let's see how it goes. Run the tests. And our 2 new tests are failing. So they're failing because we hit that to do on line 94. So the result of type checking operation should be calculated by a function called type check operation, I guess. And it's nice that Rust kind of forces us to enumerate all the possibilities. And I'm guessing we're going to need to pass in file contents and then all the stuff from the operation. I mean, I wonder whether, I'm just looking at the way these things are constructed, maybe type check tree should take in the whole tree and just know that it's, no, it's no good. All right, so it feels weird to be breaking these out, like repeating operator left, right, here, and here. But for now, we won't fix that. All right, so let's make ourselves this function. And so far we should get the same result as before because we're hitting just a different to do. And the first thing we could do is just return any, type constraint any, and that should. It's interesting that any kind of worked to be allowed for operation. I guess we're not really using it. Basically, I called it any because it was kind of like this will type check, it won't cause an error anywhere. But we haven't written any rules to combine any with other stuff. And you would have thought if you combined any with other stuff, it would come out as the other thing. But I guess in this case, we're not being asked to combine it with those things, so we're not running into that problem yet. But in a fully developed system, that any would have to have rules for combining with other stuff. But at the moment, it's just like we didn't fail, we didn't hit a to do. Because it's all quite underdeveloped at the moment. This is very, very much a nascent, let's call it, type system. All right, so what happened? So our other 2 tests, that all they needed was for you to not error. These evaluator tests are okay with us not erroring and returning any, but our 2 new tests that expect things to be all right fail at line 300 of parser.rs. Let's have a look at what that is. Yeah, okay. So we're failing at the moment where we're being asked to make our syntax tree into a string. So I guess they're trying to construct an error message and hitting some kind of problem. So yeah, we should implement this for the other types. And yeah, and I guess because this is just happening for error message display, we can probably do the trick that we were talking about earlier where it just says integer in here, and hopefully it's okay. It feels a bit uncomfortable to implement display and then do that. So we might change our mind about this being called display, and we might have our own trait for like error display or something like that. But yeah, for now we're getting away with this, and we're failing at this line. So operations, there's obviously some kind of error that we're trying to print about operations, and we're failing to print it because of this to-do here. This leads me to want to implement all these to-dos. Gosh, no, I think some of them are a bit difficult. So, all right, let's start with operation. So, leaf, we were writing out the actual thing. Operation, we're going to write out the type of it. So, I think... yeah, we've got a problem here. Okay, so this is why it's starting to look like we need the other to-dos. There's so many to-dos combining together. So we'll figure out in a second what we're actually going to do. But eventually what we're going to do is we're going to have type check, not just return nothing, but return a syntax tree that has been modified to contain type information. Now that will mean when we get to here and we're trying to display a typed syntax tree, we will have the type of the operation. We'll know what to write here. For now, we're going to absolutely cheat and write integer. And we need a big to-do here. To-do, this is lying. It's not always an integer. But this will get our test passing. And it's all about getting our test passing. So, we're still failing at line 280. At some point, we're going to figure out what's actually failing here. At the moment, we're just hitting to-dos. All right, so as well as being able to say what, like the name of the thing that's failing in our error message, we also need to say where in the source code it is. And we know how to do that, but these are to-dos that we need to implement. So here we need to actually test out span, I think. I'm writing some unit tests for span. So I know we're like 3 or 4 layers down the stack or up the stack at this point, but I think we just got to keep diving in. So our tests inside the type checking code check that this span actually comes out looking right. But here I think I want just a really dumb non-source code type unit test for the span. So span of an operation is from beginning of left to end of right. Right, something like that. So we're going to call, I think it's a span method. So we're going to say let op equal, what is this? A syntax tree. Syntax tree is an enum of type operation, and the operator is an operator token, which has a kind. Why have we made this so complicated? It's because it needs to be of type plus, which is presumably going to have a string inside it called plus, or not plus. The contents of the string is plus. And it's going to have a span that we don't care about. And left and right are both themselves syntax trees. So we need, so you can see why we don't write most of our code in this style. Because like all of those things that we need to construct to make, what is this? Leave token kind int. So this will be like the number 87, which has a span. Oh, let's make the spans a bit more realistic, shall we? Are you going to format for me? No. Okay. We're going to have the span be, the plus is going to be on like the 4th character along. 87 is going to be from 0 to 2 just in case this is a problem. I guess actually no. This is the input. This stuff really does matter because it's going to be this part of what we're testing, like that it goes from the left to the right. So we shouldn't start at 0. We'll fix that in a minute. Was I in the middle of a sentence? I'm sorry if I was. Another leaf here. Yeah. The sentence I was in the middle of was, you can see why we don't write most of our tests like this. Because it's a nightmare. It shouldn't be into, it should be to owned. That's part of what's going wrong here. Oh no. To owned. This is going to be so much easier once it stops refusing to format itself. Like now? Nope. Now, great. So we are making an operation which is a plus of 87 and 100, and we're going to move it all along by 10. And so on the other side of the plus, this is going to be from, say, 15. So about 16, and it's 3 tokens long. So I think it works like that. Now, what's it moaning about? Left and right. Are they boxes of syntax tree? Yeah, they are. Right. So I did that wrong. So we finally managed to make ourselves an operation which is just an addition of 2 integers, and we want to call span on that, and it should come out as 10, about 19, I think. So it should come out as a tuple of 10, 19, I think. If we run that test, hopefully it'll fail for us. Yep, and it panicked at the same line, 280, but that's the whole point. We're kind of chasing our way down this thing. And I guess we can probably do this in line. We can say, don't care what the operator is, but the span of this thing is left dot span dot 0, comma, right dot span dot 1, right? The left hand side of the left hand thing, that should be, I guess we can just dot it away. No comma, just dot. Don't need the ampersands, I reckon. Okay, and that maybe that test will pass now. We should also implement assignment and statement, but we don't need them right now. So let's try and get this going. Don't need the to do since we are. I guess we could test this, but it seems really basic and it's being tested by our other code, so it's probably okay. All right, that looks better. No, this test is still failing, so let's figure out why. Oh, because a span is not like a from and to position. It's a from and length, but that answer looks wrong. Yeah, I mean both. Yeah, both things. Yeah, okay, all right. All of this is completely wrong. This should be the right hand side minus. Yeah, should be. So let length equal. No, let right end. Let end equal right dot span dot 0. I guess we should put span right dot span into a variable. So basically, we were doing something completely nonsensical before. What we need is to find the end of the right hand one, which is the left of the right hand one plus the length of the right hand one, because spans are always a left and a length. And now we can say the length is end minus start. We better make start be something as well. So that start is left.span.0. And now this is going to be start comma length. Right? So that's a bit of faffing. Maybe I've like over expanded that out into far more code than it needs, but it kind of makes sense to me. You find the start, you find the end, and then you find end minus start. This is just a temporary variable to help us out, this right span thing. Alright, some more things might pass now. Still failed, because our expectation is wrong. It should be 10,9. We should just check that that looks right, but it sounds not too unreasonable. Because it's going to be 87 space, that's 3, plus a plus is 4, plus a space is 5, plus 3 more makes 8. So maybe I've done the counting wrong of where these things are at. So it goes from 10 up to 19, so that sounds right, 10,9. So I've done something wrong here. So 10 and then 2 more makes 11, 12. So this should be at 13, 1. And this should be at 15, 3, and then it will indeed be 10, 8. And I think that's going to work, right? Yes, okay, so that test failed, and we've still got only those other 2 tests. Sorry, that test passed, we've only got the original 2 tests failing. So, let's look at the one that thinks it should be okay, because 19 plus 21 is now 32, and that's actually failing because this returns any, I think. What did we return from this? I think we returned any from there, and that's not the same as I32, and I think that's why it's failing. And the name here is integer because we've cheated and just made it be integer. So let's have a look at what we actually returned for type checking and operation. Yeah, we said any, and that's wrong. Basically, in this case, so far, it's just going to be the type of the left-hand thing. Like all our operations at the moment only add up things that are the same as each other, so this is all going to be fine. I guess we could put in some kind of to-do about more complicated things, but for now we can just say please type check the left hand thing, and that's it for now at least. Operations just have the same type as the left-hand operand. Oh, I've just thought of a case where this isn't sufficient, so that's good, isn't it? So we'll write a test for that and get it passing. So we'll ignore the operator and we'll ignore the right-hand side, but we're about to make use of the right-hand side. So now will some more of our tests pass? Yeah. So our test where it's all okay is now passing, but our error isn't quite looking how we wanted it to look because I've spelt that wrong. So where are we? This should be in our type checking. Yeah. So expected F64 found integer is certainly part of the problem. Yeah, all right, so we've done it. We've got that test, all our tests passing, so maybe we should think about doing a commit, even though there's some stuff that's very much not done yet. This is really cool that we're able to produce an error message as smart as this, isn't it? Although we are lying here. But what did I leave feeling very unsatisfied about? Oh yeah, it was that an operation in itself should check that the 2 types that we're adding up or whatever actually are compatible, which in this case means they have to be the same. So we need another test for our type checker. Yeah, because we were really focused on just type checking this one type of operation, but now we can try something else, which is, I guess we've already got a test for adding stuff up, although we could, yeah, let's do it. So first of all, let's say type checking an operation on two identical types is okay. So basically it's just the 19 plus 21 case, although we will always, as always, change the numbers. That should be fine. Let's just check it is fine. Did I actually run an extra test? Yeah, 59 passed, 60 passed. There we go. And now we want something which is going to fail like this for when you try and add up two things that are different types. So this should be adding two different types is an error. And it's just going to be, let's say 1.0 plus 998, right? So you can't add those two things up. Now let's see what Rust says when we try and do that in our program. So can we just have a statement like 1.0 plus, what did I say, 999? 998. Don't know why I said that. You can't. Oh, yeah, we can. All right, so it says, cannot add an integer to a float. And then it gives, oh gosh, it gives us a whole load of other stuff, which we're probably not going to do. But it would be good to have something that looked a bit like this getting printed out. So paste that in, and then we're going to have to tidy it up. And we'll just leave this in for reference for a second. Oh, it's all messed up. Anyway, so it's not going to say an error code. Just going to say, cannot add an integer to a float, I guess. Oh, it's going to have that X thing in it, right? That's what MEAT does, I guess. So we'll put that in, see if it comes out right. Cannot add an integer to a float. And this line is going to look similar to this. It's going to be somewhere, we don't know where lefty righty this wise, it's going to say somewhere in some position in standard in, which is what we're calling the thing. It's going to say, well, it's going to use the MEAT style pipes. And it's going to say no implementation for float plus integer. Oh, that's going to be a problem for us because everything is called integer at the moment. Oh no, that was for operation, so we might get away with it, or we might not. And all of this needs to have these end of line. This is a bit painful, isn't it? All of this stuff at the end of the line. Something like this, and we're going to get the actual number of spaces completely wrong, but that's okay. And I don't know where our double quote is going to end up. Somewhere, maybe lined up with the old double quote is the right thing. Yeah, it looks like it. So right now, I think this is going to be fine because it just ignores the fact that we're adding up two incompatible things right now. So this test is going to fail because it was expecting an error, but actually it wasn't. Okay. So we need to actually do our type checking on an operation and not just, so we need to say left type is this, and right type is this. Oops, not that. Which means we actually need to use our right variable. And we obviously need some semicolons. And if they're fine, we're going to return left type. I guess we're going to return OK left type, because left type is going to need to be actually fail if something goes wrong. What are you moaning about? Oh, I got a semicolon there where I shouldn't have one. That's what you're moaning about. Okay. So we found a left type and the right type, and we're returning a left type, but no, we first need to check whether they're the same. So if do they have to be the same, or do they have to be? Yeah, they have to be. For now, they have to be the same. Can we even compare left and right? Can we even compare type constraints? It seems that we can. Then we need to return. I guess this should be, if they're equal, it's okay. And if they're not equal, we need to do something explaining that some things are wrong. So let's check type check assignment, where we do some errors. Yeah, and the other thing is we could say, do they combine? That's what we said here. But I think in this case, for now at least, operations require them to actually be the same, not just combine. I'm not sure what combining would mean for an operation, so we'll try. We just won't think about that yet. We'll think about type mismatch is not. It must be a new type of error. This, which is, well, let's look at what our error message should say, because that will guide us. It's cannot perform operation or something like that, I guess. And then we'll have to flesh this out. When we have different types of operation, we'll have to flesh out what exactly we say here. So let's go with, I guess you could say like invalid operands, or incompatible operands, or just cannot combine. Let's go for invalid operands, and we'll hopefully, if we don't like that later, we'll change it. So we're going to have a new type of error called invalid operands. The source is going to look like this. And then the other things it's going to ask about, we're going to have to figure out in a second. So let's first of all make ourselves a thing called invalid operands, which is going to look a lot like type mismatch. So invalid operands, and the explanation, the main explanation, where it said mismatch types before in the other thing, it's going to say cannot add integer to a float. It's going to say something like that. I mean, for now we can get away with that for this test, but what if it's the other way around? So I think we want to say cannot add right type to a left type. We'll see whether we can do this. Well, okay, so far that's pretty encouraging, because it suggests to me we need a left type and a right type here. And we still need a place in the code, and I'm not sure whether we need any more. What label do we need? We need some kind of label, right? We need no implementation for blah. So we need something like this. And again, we'll need left type and right type, so that's quite good actually. It seems like it's not too bad. No implementation for left type plus right type. Now the fact that this all says plus right now is obviously wrong. Or not, obviously not general enough for us, but we'll see. And I think there's only one label, right? Which is expression. I think this is going to be, this is actually kind of pointing at the operator. So maybe it should be operator, maybe operator, or maybe operator span would have been a better name, but we'll see. So when we're making an invalid operand, we need to provide a left type and a right type. Can we call toString on these, or are we going to have to implement that, or is that the wrong way of thinking about it? I think it's probably the right way of thinking about it. And then the location of the operator is literally going to be operator.span, where we need to rename operator to not be unused anymore, because it points at the operator. Okay, hold on. Operator token doesn't have a span. Oh, did I just want span without the... I think there's is there an into? How are we doing this on other stuff? Yeah. A span is a source span, which I can just turn into. No, sorry, a span is a tuple, but if you call it into on it, it gets turned into one of these source span things, so that's fine. But we don't currently have a way of turning type constraint into a string, but we definitely should. And again, we probably want unit test for that function. But yeah, so where's type constraint defined? Let's jump to its definition. So we've got an impl type constraint, but we haven't got an impl display for type constraint. Impl display for type constraint. And give us an implementation. And for now, let's just do f.writeStr to do. And that will at least tell us that we've got somewhere near what we should be doing. Okay, so this is interesting. We've made another test fail because we're now type checking operations, which we didn't before. So so we're going to have to deal with that. But in the case of our test, we have got a string that looks reasonably close to what we wanted. We've got obviously these to-dos put in instead of integer and float. And the line numbering looks messed up and things like that. And we haven't got the same formatting here. So other than the to-dos, the rest of it is formatting. So we won't address this problem yet, but we'll try and get this error message looking right. So first thing to do is make our display for type constraint actually come out okay, and I guess we want some unit tests for this. Why not? We like our code to be properly tested, don't we? So I'm tempted to write just one test for all the different ways of displaying types. Maybe that's lazy, I don't know. Can display type names of types, let's say, and assert equal so this is going to be, if we make a type constraint called float, so let's say names of I guess they're literal types, these that we're worried about so far. So type constraint float dot toString should come out as float, and type constraint int.toString should come out as integer. Maybe we should have called this integer instead of int. So that should fail because they both come out as to do. So let's make them pass by finding somewhere we did impl display. Yeah, here we are. So for now, we can do this in a really dumb way. Match self. And leave many of these as to-dos. I don't know why it's still generating weird code for us there. But in the float case and in the int case, we'll just return something useful. The reason I'm leaving these to-dos around is I honestly have no idea what we should do in most of these other cases. So we're just going to not think about it and think about it later. Like for me, a lot of programming is just figuring out a way to not have to think about something until later. And like, I think to some people watching that might be quite like stressful or lazy seeming. Oh, this should be all wrapped up in some kind of result. Oh no, in fact I'm talking total rubbish. Yeah, like, is it just because like I'm not intellectually capable of thinking about everything at once? Maybe. But this is a way of getting stuff to work. What I meant was this. And it's a fairly tried and tested way. Like, no one is intellectually capable of understanding a large program in full. I think definitely some people are intellectually capable of holding a lot more in their brain than I can. Hold on, I think we can just return this result of calling write_str. Later that might cause us a problem, but for now they're both doing exactly the same thing, so they both return the same type. Yeah, so I'm all right at holding in the context of a sort of 5-line function in my head sufficiently to understand it and check whether it looks all right. I'm not capable of holding certainly a program the size of what we've written so far in my head, so I'm desperately constantly trying to shrink it down into a context that I can fit in my brain, and the way I do that is by writing unit tests, which is why I just bothered to write this kind of fairly meaningless looking unit test. By the way, maybe it's obvious, but if you call toString, what actually happens after a few layers of indirection is you end up in the implementation of display for that thing, which calls the toString calls the format thing, passing in a formatter, and we write some strings into the formatter. So now our display name should come out okay, and our error message is now looking better. Cannot add an integer to a float, which is what we expected it to say. So it's all looking not too bad. There aren't enough spaces after that, so we can fix that. Where were we? Here. So hold on. What was it? There was not enough spaces before the stood in line. It needs like 2 more. So let's do this. Just do this piece by piece, shall we? And then it should be 1,5 instead of 1:8. Because this is like the 5th character in 1, 2, 3, 4, 5, right? So that makes sense. And then there should be a 1. Really? Where should the 1? Oh, it should be a 1 instead of a 2, yeah. This is line 1 of our program. Something's up here. We've got extra. The 1 should be the other side of the line. Right? I guess the 1 should be here, and then how much space is there before the... How is this? Oh, there's like an extra new line in my. Oh, I'm now lost on which one is the code and which one is the actual error we're seeing. I think there's no, the real code. There's no extra line. It goes straight in like this. And there's 2 pipe symbols. Really? Well, I guess so. Like this? No, I was wrong about where the one was. The one is on the other side of the line, like it was originally, and I was getting confused. Right, so now it's looking not too bad. What comes next? Now we have dots there instead of lines. There's a gap with just a dot. Is that right? I mean, not without more spaces for sure. 2 spaces there. And then this should have something like that. 3 maybe. Fascinating watching this, isn't it? And this should be... Oh, no. No, well, there isn't a new line there. Oh, I see. Well, this is a dot. And then... Yeah, it's indicating the plus symbol, isn't it? Of course. So it should be... Here, there should be this symbol. That didn't work. Try again. Yeah. Instead of the arrow. And it's all actually on the next line. That we say another dot and then no implementation. Is that right? Yeah. Another dot and then like a curvy line symbol. And then blah. See how that's looking. It's looking not too bad. We shouldn't have curly brackets around these. Should just look like that. Right? Or hang on. No, there were curly brackets. So we need to fix our actual code to make that work. All right. And there's also a couple more spaces there. So let's go into our actual code and make it somehow display brackets for us, which I think might be that you have to double them up to say don't escape it, but don't treat it as a substitution, but I'm not sure. It doesn't like that. Right, that wasn't it. Let's try backslash to escape it. Definitely doesn't like that. Do we have to double them up on both sides? Of course, I don't know whether this is just a normal format, string format, or something else. So. Okay, that looks good. That was working. All right, so there also should be back quotes around it. So this is looking pretty good now. Oh, it's these dots are definitely wrong. Let's do them properly. They don't look right here anyway, do they? That's definitely not right. Is that it? Yes. Okay. So we're doing well. Interestingly, our failure messages become a lot less helpful on the remaining test that is failing. So we had an assignment setting a variable value. Panics at line 46 of type check because we don't know how to display any constraint. Okay, so I guess we can write out any here, but that's definitely not going to be the final answer to this because like it's printing an error. It's just that this error is going to have something weird inside it. So yeah, we need a way, I think, of just saying, for now, don't try and type check this because it's too hard. I think. Because we haven't yet found out the type of this. So I guess we can just say if the left-hand side is any, ignore it for now. And that'll do us. So long as we've got a to-do there. So this is in type check operation. We need to say if left is right, then we're okay. I guess we can put in an else if left type is any. Then we can do some kind of to do. For now, ignore. Don't check because left hand side is not type. I guess this is because the type checking of the left hand side is not yet done. So we'll just say okay, left type. And for symmetry, we should probably do the right hand side as well. I think it's okay to just return left type. I think we'll get away with that for now at least. All right, so we've got passing tests. We've done quite a bit of stuff. I think we've probably gone on too long for this video, and we've got type checking to the point where it's actually working. Let's try passing in an expression and see whether it now works. Yeah, okay. So you can now add 4 plus 3 and get 7, and I think we can also ask for x after adding them up, and that's okay. Can we also add 1 to x? I can't remember whether we've implemented this or not. Yeah, we can. So you can make a variable called x, you can add 1 to it and get back the answer. So that all works with some type checking. There's a bit more that we haven't filled in because the type checking is only being done on the happy test at the moment. So maybe we'll look at that next time. My general plan, by the way, from now on for a little bit is to try, once we've figured out some of the to-dos that we just need tidying up, we want to try and flesh it out into a language that you can use to do really basic actual programs in. And then we'll start thinking about loops, functions, stuff like that. But first of all, flesh it out enough that you have got actual numbers, and maybe you can, I don't know, maybe even print some stuff out. You can't do a lot useful without that. So yeah, it's something that makes it feel like it's almost a kind of a programming language, even though it's very basic. And then some more of the more advanced things. And we're getting into, like, especially, I'm really excited about getting into type checking, type inference and stuff like that. So we'll get there. Hope you're enjoying the series. See you next time.